All right, guys, I'm going to give you a quick run through on section 8.4. Let's see, this one won't be too bad. We did all the kind of heavy lifting in 8.3. So if you remember in 8.3, we discussed the power series method. We went through a bunch of stuff with that. And in this section, we're essentially going to do the same thing. There's one extra thing we're going to talk about, but the focus of the power series method, what we used it on in section 8.3 was homogeneous first and second order equations with polynomial coefficients, right? Polynomials right there. So it turns out you can use it for analytic coefficients too. So we're going to talk mostly about that. We can also include a forcing term on the right side of the equation, but that also has to be analytic, and we'll get to that shortly. But first, we're going to talk about something else. We'll be able to solve homogeneous equations like this where the coefficients are now analytic. So that's going to include things like cosine x and sine x, and that's a polynomial, which is analytic as well. So, and then as I was saying, we can also extend this to non-homogeneous equations with analytic coefficients, but the forcing term also has to be analytic as well. Remember, analytic means it can be expressed is power series. It's equal to its power series on some positive radius of convergence. Okay, but before we do this, we're going to talk about an issue that we ran up against in the last example of 8.3. So if you remember in this example, we solved a differential equation and we weren't able to get a closed form solution. And what I mean by that is we couldn't find a solution, we couldn't find a pattern in the coefficients which prevented us from figuring out a formula for an, which means that we couldn't write our solution in sigma notation. And if you can't write it in sigma notation, closed form, then you won't be able to figure out what the radius of convergence is. So, and that's kind of a problem because, yeah, you have the solution and that's great, but without knowing the radius of convergence, you don't know where the thing's valid. Obviously, there's some positive radius of convergence where it is valid, but that radius could be so small where effectively the solution that we found is pretty much meaningless if we don't know where we can use it. So there is this thing we can do. There's this theorem which will basically give us a minimum bound or a lower bound on the radius. So it'll give us at least something to work with. So that'll be the first thing we'll talk about. So it's better than nothing. We won't know the exact interval of convergence, but at least we'll have a lower bound on it. So here's the theorem. I'm not going to go into the theory behind it, but basically it says that if x naught is an ordinary point, now this is for a second order equation. So that means p of x and q of x are analytic at x naught. Then there's a power series solution exists, so we can use the PCM. And its radius of convergence is at least as large as the distance from the center x naught to the nearest singular point. Now, we have to include, in order for this theorem to work, we have to look at singular points that exist in the complex number plane. So we're going to extend, we've been working with real numbers, but we have to extend this to include complex numbers. So I want you to try and picture the complex plane in your head. I know it's been a long time. We have a real axis, right? You have an imaginary axis. It's kind of a Cartesian coordinate system. And basically what we're going to do is find all the singular points, and we'll find the distance from the center to the closest one, and that will be our minimum radius of convergence. And that's something, right? It's a lower bound on the radius that we can actually use. By the way, in addition, I guess we could have mentioned this in the last section, but because this one is second order, the solution that you'll get will have there's two linearly independent solutions, and they're both going to be of this form. And we could find each of those linearly independent solutions. There's a bunch of them, right? But we could find two specific ones by setting whatever we get for the solution using the PCM, setting A1 equal to 1 and A naught equal to 1 and A1 equal to 0. That'll give us one linearly independent solution. Or we could set A naught equal to 0 and A1 equal to 1, and that'll give us the other corresponding linearly independent solution. Okay. So essentially what this means is, for second order, we can break down our solutions into this form. By the way, when you see it in the power series form, that's going to be an A naught, and that's going to be an A1. All right, but we'll come back to that. We were talking about that in the last section a little bit. So, but for the first two examples, we're going to find some lower bounds to determine a lower bound on the radius of convergence of a power series solution, which we would have gotten using the PCM. So for example, let's say we've got this second order. This one's got some analytic coefficients. More specifically, they're polynomial coefficients. And let's see, we want to find the minimum radius of convergence of the power series to the solution about 0. So we're going to center the solution about 0. So the theorem basically says that all we have to do is find the distance from 0 to the nearest singular point for this guy, and that's going to be our radius. So what we should do is find all the singular points. So we know how to do that. You move the equation into standard form and identify your P of x and Q of x. So hopefully you can do that. Just divide the equation through by 2. And you'll notice that these guys are defined everywhere. So there's no singularities. Even in the complex plane. I mean, the only problem would be if the denominator was equal to 0 for these, and it's not. So there's no singularities. That means the distance from 0 to the nearest singularity in the complex plane is infinite. There's no problems here. So that means that the radius of convergence of any power series solution that we get using the PCM is infinity. Okay. All right. By the way, if you're curious what the solution to this would be, if you were to use the PCM, you could actually do it to get some practice. You could check your solution using this code that I supplied right here. And this will give us, there's your, by the way, asymptotic D-solve value will tell us the power series solution up to a specific degree that we tell it. And so here's the second order differential equation. We're solving for y. The independent variable is x, the center is 0, and we want the solution up to degree 7. So what it's done here is it's written out the power series solution. It's kind of separated out into the terms that involve A naught and the terms that involve A1. By the way, it should be no surprise that there's two arbitrary constants right there, because this is a second order differential equation. Okay. So you could do the work just to get some practice and check your solution, at least up to degree 7. All right. So if we were to use this thing, out in the real world, and you were to give it to an engineer, you could tell the engineer, this thing has a radius of convergence of infinity. So, depending on how fast this converges to 0, maybe you should tell them something like, as long as we stay close to the center, you should be okay, because these things converge to 0 pretty quickly. The further you get away from 0, the worse it gets. Of course, if you had all the terms, if you had the solution in closed form, then you could give them the exact solution, Okay, so let's do one more interesting. So in that last example in 8.3, we used the power series method to find a solution to this guy. So this was that problem one where we went through all that work. We couldn't find a formula for the coefficients, but we were able to calculate the coefficients up to degree, it looks like 6. And so we wrote the solution. It wasn't in closed form, and we separated all the A naught terms from the A1 terms. And we were able to get it in this form. It's a nice form when you have it separated like this, because it tells you the two linearly independent solutions you could use. That's a pair that would be linearly independent. So we weren't able to get the thing in closed form. So we couldn't find the radius of convergence for this thing. Let's use that theorem to find a minimum value for the radius of convergence. So this is really easy. You just take a look at your original differential equation and you find the singular points. So if you get the thing in standard form by dividing out by 1 plus x squared, then you're going to have this guy. There's no removable singularities or anything, so we just leave it. So there's p of x and there's q of x. So what you want to note here is that these things will fail to be analytic where on their outside of their domain. So, you know, there's really no problem here in the real numbers. However, if we're talking about the complex plane, if x equals I or negative I, that is if, let's see, 1 plus x squared is equal to 0 and you solve for x. So if x equals plus or minus I, you're going to have a problem. You're going to be dividing by 0. So that means you can think about I and negative I being singular points in the complex plane. So let's graph these in the complex plane. So in the complex plane, you have a real axis, which is usually written horizontally, an imaginary axis, which is written vertically. And so the imaginary axis would be the axis which counts i's basically, and then the real axis would be the axis that counts ones. So this would be 1i, and that would be 1, 1. So let's see, our center's at 0, and we found that there's 2 singular points, one here and one here, and the distance from 0 to the nearest singular point, well, they're the same distance, but it's 1. So what does that mean? That means that the radius of convergence for our power series solution here is at least as big as 1, right? That's the minimum it can be. So that means that all the partial sums of the series will converge so long as, you know, we're in this interval, which is the same as that, right? So it's something, right? So then you could pass it off to the engineer and be like, okay, you're safe to use this thing as long as you're, you know, in this interval. Now, the actual interval of convergence may be larger than this, but there's no basis to make that decision based upon the theorem. We don't have anything really else to use to zero in or to figure out exactly what the interval of convergence is. Without the closed form, we're kind of stuck. But we do have that theorem, so at least this is something. It's better than nothing. Okay, all right. So that's minimum radius of convergence. All right, you know, all of the power series problems that we've been giving you, we've been asking you problems that have been centered at 0. You know, you can center them at other points. You kind of have to modify the steps of the power series method a little bit. I mentioned that earlier, but I think all the problems I've given you so far have been centered at 0, just to kind of get you used to working with it. You can center it at other points. The math becomes a little messy, so we kind of avoid it. But there is a cool technique where you can solve for power series solutions about other points other than 0 by kind of temporarily shifting, finding a related problem solved at 0 and then kind of shifting it back. So I'll show you how it's done by example. So we're going to use the power series method to find, let's just find the first few terms of the solution to this guy, but we're going to do it about 1. All right, so your power series solution, you know, is going to look like this, right? And we're guaranteed, you know, there is a solution. So our job is to find all of the ANs. By the way, we know 1's an ordinary point, so that's why we know that there's a solution. As far as the radius convergence, once we find it, there's no singular points because P of x and Q of x are analytic. So the radius convergence, whatever power series solution we get, we know that it's going to be valid everywhere. So once again, there's our solution. Our job is to find all the coefficients. So here's what we'll do. The problem if we get this x minus 1. So what we can do is kind of shift the power series kind of temporarily from 1 to 0. Right now it's centered at 1. So the way we're going to do that is we're going to do a little change of variables. I'm going to let t be x minus 1. All right, so I'm just going to rename x minus 1t. So what'll happen here is all the x's get replaced with all the x minus 1s get replaced with t, which means that x, if you add 1 to both sides, gets replaced with t plus 1. So now we've got this power series centered at, in terms of t, centered at 0, right? So now we're going to define a new variable. We'll call it y, just to kind of get rid of this, capital Y. And we'll define capital Y of t to be lowercase y of t plus 1. So this is the power series we're interested in. All right, and it's a power series centered at 0. So what you want to note is, look, if we look at the original power series here, what we would need is we'd need the first two derivatives of it. And you'll notice that y of x is equal to y of t plus 1, which is equal to capital Y of t. And the same thing with the derivatives. And by the chain rule here, we know that y of x is equal to big Y of t, y prime of x is equal to big Y prime of t, y double prime of x is equal to big Y double prime of t. So substituting these into the differential equation, we've got this equation in y. So we're going to get a solution that's off by a unit, but it's easy to fix. So, and it's going to have a solution of this form. And the coefficients that we're finding are the same coefficients that we wanted with the original problem. So we can solve this thing, right? So we would just solve it the normal way. And we'd arrive, using the power series method, we'd arrive at this solution. So everything looks good. This thing's centered at 0. We know its radius of convergence is infinite, so it's good everywhere. Of course, we don't have it in closed form, but we only want it up to degree 3, so that's okay. And then to restore the solution, we'd simply make the change of variables back, since x was equal to t plus 1, then t is equal to x minus 1. So we just replace all the t's with x minus 1s. And you'll notice now we've got a power series solution centered at 1. Notice all of the powers of x minus 1 there. And the radius hasn't changed. So we're still good. So there's your power series solution. Now we could check our solution here. If you plug the original differential equation in here and you want to find the solution about 1, here's the code that will get it for you. Again, you don't need this traditional form. I could take that off there. Just makes the answer prettier. So there's your differential equation. There's your dependent variable you're solving for. There's your independent variable. There's the point you're looking for, the center. This is how many the degree to which we want to go, which we want to show. So this is an approximation, right? This would have to be infinity to get the exact solution. This just does a naming scheme to set up the names of these guys. We use A0 and A1 in this class, so that's this. So just leave that alone. So let's see, let's check it out here. Yeah, it looks like they rated it a little differently, but it's equivalent. So we're all good. So we found the solution. Okay, so that's a way to find power series centered at points other than 0. So now let's use the power series method on homogeneous equations with analytic coefficients, and then we'll build our way up to include analytic coefficients with analytic forcing terms. So it turns out it's kind of what you would expect. Basically, if you have something like this, let's go ahead and use the power series method to solve this one. This one's an initial value problem, so it's not really any different. We're just going to use this for A0 and that for A1. So everything's pretty much the same. We're going to center it about 0. And we're also going to determine the radius of convergence. So we can determine this on the outset. The radius of convergence, you just identify the P of x and Q of x and see where the singularities are. And there's no singularity. So, the distance between 0 and the nearest singularity is infinite. That means whatever solution we get for the power series method, we know the radius is going to be infinite. So we'll just get rid of that. So that part's done. All right, now we know that there's a power series solution about 0, and we know it has this form. Okay, our job is to find the ANs. So we do this kind of like we normally would do it. We're going to need the first couple of derivatives, the 0th, the first, and the second derivative. And we're going to end up plugging those in here. Now that guy's a polynomial, so we can leave that guy. However, this guy, e to the x, that's an analytic function that has a power series expansion. Actually, it's a known power series expansion. We could look this up in our table. There it is right there. There it is expanded out, and there's no qualifiers on it, so it's good everywhere from -infinity to infinity. So we're also going to substitute this guy in. So if we substitute all the derivatives and we substitute this in for e to the x into the differential equation, there's what we get. So now for the kind of harder part. This is, again, I mentioned this in class. You want to make sure that you're writing very carefully, being really careful with your indices, because it's easy to mess up just one and it's going to throw off your whole solution. It's like a programming class. If you mess up one little character, your code doesn't compile. Same thing here. So here's the problem here. You know, this middle term, that's going to be somewhat difficult. I mean, it'd be easy to push the 1 plus x squared through in there and distribute, but this guy in the middle, that is an issue because, you know, it's hard to figure out exactly it's hard to figure out a closed form. You'd want to get just a single sigma representation of this, and there's not a nice way to do that. So what we'll do, let's see, is let's just go out a few terms. Instead of finding a closed form solution, let's go out to, let's say, degree 4. Yeah. So everything that we expand, we're going to expand out to degree 4. So let's go through the whole thing. Let's start with this. So you're gonna write this out in expanded form and just go up to degree 4. Of course, the pattern would continue. I'm not going to walk you through all this. I think you guys can figure this out on your own. I don't think it's really that helpful for me to try and do it for you. And then we're going to go to this guy. So, okay, what would you do if you were multiplying these guys out? Well, that's a polynomial. It's an infinite type. That's a polynomial. So when you multiply two polynomials, you effectively take every term in the first poly times every term in the second poly. So what we could do is take the 1 and distribute it through the polynomial over here. And then take the x and distribute it through to this polynomial. And then take this guy and distribute it through to that polynomial, and kind of do this term by term. And that's what I'm showing over here on the left. So I started writing out some here. Now, let's start with this one. If you write out the first few terms up to degree 4, that's what you'll get. We'll stop at degree 4. And then for the next one, up to degree 4, that's what you'll get. For the next one, you have to push that inside, right? Write out the first few terms up to degree 4, and then up to degree 4, and then up to degree 4. And here's how we know we don't really need to add, we don't need to do any more. It's, you know, there's not going to be a degree 4 term on anything after that. So we can stop about there. We're also going to need to expand that one. That one's easy because we just push the 1 through and the x squared through. So there's the 1, there's the x squared, and we find the expansions up to degree 4, up to degree 4. All right, so now what? Well, remember the idea here is we're going to add all of these guys up on the right, and we know the total has to be 0. So we set it equal to 0. So it's going to be some big, long polynomial. Now, a lot of these, there's going to be like terms there. So we want to collect all the like terms. And then we want to set all the coefficients equal to 0 by the vanishing term. So we can kind of do this all at once if you can kind of follow along here. What I'll do is I'll find the coefficients of each one of the powers and just set them equal to 0. So let's start off with the largest one. That would be the x to the 4th powers. So I have all the x to the 4th here. So what I want to do is add all those terms together. And since they all have an x to the fourth in them, we can just add all the coefficients. And if we do that, we'll get this guy, and we'll set them all equal to 0. So that would be for the x to the fourth term. We would do the same thing for the x to the third term, x squared, x term, and constant terms. And if we set them all equal to 0, then there's our infinite system, right? Well, it's not infinite because we're only going up to degree 4 here. So, but there's our system. Okay. So now one thing we know, because this is an initial value problem, we know y of 0 equals 1. So we know that a naught is equal to 1. Okay. And we know that y prime of 0 is equal to 0. So that tells us that a1 is equal to 0. So that means we could simplify this system quite a bit. We can set the a naughts equal to 1 and the a1s equal to 0 to kind of simplify this. So it looks something like this. And then we could solve for the remaining coefficients. So start with a2, solve for that one, and then solve for a3, and then solve for a4, and then a5, and then a6, so on and so forth. And we'll stop there. We're only doing the first few terms. So now we can write out our series solution to the IVP. So this is going to give us a solution up to order 6 because we solved up to a6. So fix that little guy while I'm here. So there they are. We just simply plug them in. So there's your solution. And we should maybe simplify this a little bit so we can kill that 0 there. So there's our solution. And we already proved it has an infinite radius of convergence. Okay, now we don't have the closed form of the solution, but that's okay. A lot of these problems I'm not going to ask for the closed form. I'm only going to ask for the first few terms. So if you wanted to solve this problem using the Wolfram cloud, there's a way you can solve initial value problems too. So I wrote the code down here. Here's the corresponding code. So it's the same function, asymptotic desolve value. You write in your equation, make sure you have the double equals, make sure all your formatting is correct. For the exponential function, it uses x of x. There's your two initial conditions. Make sure you use the double equals. The dependent variable is y, independent variable is x. We're centering around 0, and we're finding the solution up to degree 6. So there's our solution, and it does match. It does match with the solution that we found by hand. So I want to emphasize, you guys can use this program to check your work, but be careful because, on the exam, you won't have the program. So I would use this as kind of a check. I would work through it by hand. And then when you're done, check it. If it's off, see if you can find your error, go back and find your error. Okay. All right. Also, if you have any problems with the code, reach out. You might be able to figure it out on your own, but if you can't, just reach out and I'll give you some pointers. Or if you want to see some visuals, show you how to make some code so you can visualize some of these power series solutions. All right. And the last thing. So not only can we do homogeneous equations with analytic coefficients, we can do homogeneous equations with analytic coefficients with a forcing term, as long as the forcing term is also analytic. Okay. So G also has to be analytic at x0. Now in this context, we kind of adopt the definition that when we say an ordinary point, we mean that P, Q, and G have to be analytic at x0. Okay. Yeah, so this guarantees a power series solution about 0, about x0, I should say, depending on what x0 is. It's usually 0. So that justifies the use of the power series method. So let's go ahead and do it. So there we go. We got a second order non-homogeneous, right? It's linear differential equation. The non-homogeneity is sine x, which is analytic. X is analytic. It's already in standard form. 1's analytic, or -1, right? So there's no singularities or anything. So everywhere is an ordinary point, including 0. So we're going to have, we can use the power series method at 0. We're going to get a solution. Let's go ahead and determine the radius convergence that we would get. So as I said, there's no singular point. So the distance between 0 and the nearest singular point is infinite. So the radius convergence of the solution that we're going to get is going to be infinity. So we know that the solution has this form. Let's just go up to degree 7 here. We don't have to determine a pattern. Make this a little easier. Yeah, you would write this out up to degree 7. Our job is to find all of the coefficients, right? All of the ANs. So we kind of proceed like we always do. It's a little more messy because you've got a left-hand side and a right side. You're basically going to take both sides, express them as series, and rewrite them. So you have a polynomial equals a polynomial and then equate coefficients. It's the same idea. So, you could work through this on your own, but basically it's the same idea. On the left, that's what you'll get. And you could, rewrite the thing. This is sigma notation, but I only want the first few terms. Let's see. Oh, I wrote out x to the third. What happened there? Well, I might have left out a few. Yeah, I guess I should have written out some more, but in any case, you get the idea. On the right-hand side, sine x, yeah, over here we'll go out to degree 7, so we should do the same on the left. In any case, what ends up happening is, oh, I think I left it out because I just didn't have room. It was going to spread off the page, but you should go ahead and do that yourself. You're going to have a poly equal to a poly. And it's the same idea with the vanishing theorem. You equate coefficients on both sides. So if you equate the coefficients, the constant term right there, there's no constant term on the right. So that's equal to 0, which allows us to solve for A2 in terms of A0. By the way, A0 and A1 are arbitrary constants because it's a second order equation. So everything should be in terms of A0 and A1. And then we set this guy right here equal to 1. Solve for the larger index. And we do that for the rest of them up to A7. So, right, yeah, A7, yep, to get the 7th degree. And then we just simply plug them in. So there they are. All right, now for the interesting part. There's our solution, but it's often helpful if we can kind of decompose the solution so it looks like the solutions that we would have got using like chapter 4 techniques. So let's start by separating out the A0 and the A1 terms. So we can do that. We can separate out all the A0 terms here, and here's all the A1 terms. And then what we can do is we can further separate out some constant terms over here, or some terms that don't involve A1, like so. So what you'll notice is if I take these guys and factor out all the A0s, take these guys and factor out all the A1s, and then kind of leave this left over on the end, what I've got is I've got a constant times y1 plus a constant times y2 plus this other function. This is kind of what we're expecting. If you remember, a solution to nonlinear equation is going to have this form. Remember from chapter, what was it? Oh, use C is just because we used that in the old other chapters. C1, I think I used C1 and C2. Is that right? Something like that. Doesn't have to be. In any case, yeah, it's a homogeneous YH plus YP. It's the same thing that we always get, where Y1 and Y2 are linearly independent. So those two are linearly independent solutions. All right, so this should be no surprise. And it's kind of nice that you can kind of write it in the same form. By the way, if you wanted to solve this using the Wolfram Cloud, you could do it. This one's pretty straightforward. I'm doing this up to degree 7, and it looks like it even factors everything out for me. So there's your A0 terms or A1 terms, and there's your the rest of them basically. All right, so this section really, there's not too much new. The problem is going to be the organization of writing everything out and basically being really careful with all of your indices and your calculations. You really want to find a way to keep everything super tight and organized. And I would advise you to do that on your next exam too, because trying to grade these is pretty difficult for me. So if I can't read your work or I can't follow it, that's not going to be good for you. So find a way to write it nice, consistent, and organized. I would probably advise you to do it the way I've done it, but if you can find in these notes, but if you can find a better way, you can do that as long as it's very clear. Maybe line up your equal signs. You'll notice I kind of did that here. I always like to do that. It's pretty standard. Kind of line everything up so you can kind of quickly. That's a nice thing about lining up equal signs. You can kind of quickly see everything. When you write the equal signs left horizontally, these equations next to each other, it's hard to reference everything. This is more easier to reference. All right. Okay. Hopefully that helps. And if you have any questions,